So we started looking at calculus last term. Now we're going to look at it in a little bit more detail and how we apply it to geometry or curve sketching, putting it on the number plane. So the first derivative, and remember there's all these different notations we could use, y dash or y prime as some people say, f dash x, d dx, and we actually write the function in the parentheses, or in that case braces, or dy dx. And it measures, well, when we're talking about curve sketching, it measures the slope of a tangent to a curve. But basically it measures a rate of change. So in curves, rate of change is slope. How does y change as x changes? So things we can tell from a graph just by looking at the derivative without even drawing the graph. If that derivative is positive, then we know the curve must be going up or increasing. Now, why is that? Well, if my tangent has a positive slope, then the curve has to be going up. It's impossible for it to be going down. And so consequently, if the derivative is negative, we know the curve must be going down because the tangent has a negative slope. If it's neither positive or negative or equal to zero, we come up with this very creative, it's stationary. It's not going up, it's not going down. It's a stationary point. It's all right. Just using the first derivative, we're going to get a very rough sketch of this curve. So it's 3x squared minus x cubed. We're going to find those stationary points. We're going to work out their nature. And by their nature, they mean, well, is it what we call a maximum turning point or is it a minimum turning point? And then we'll, as I say, draw a rough sketch of that curve. So we're going to need our derivative to find stationary points. So when you're doing your working out, so you explain what you're doing. Don't be late. So the first thing you write down there is, well, after you've worked out your derivative, of course, stationary points occur when the derivative is equal to zero. You're explaining why you're going and solving this equation. Right? Why did you make this derivative equal to zero? What are you doing? So you're explaining yourself. Okay, I'm going to go and find these stationary points. And I know that happens when the derivative is equal to zero. So there's the equation we have to solve. So we have 3x outside of 2 minus x is equal to 0. So either x equals 0 or 2. So we have two stationary points. And we can work out the y value. Now be careful, make sure you substitute into the equation that says y equals, common mistake. Well, it is a common mistake. People substitute it into the derivative, and consequently, what value do they get for the y value? Of course, because it's a stationary point. Now, of course, we know this is a polynomial, and we know it is a continuous curve. So logic tells me which one would be a minimum and which one would be a maximum. Which one would be the minimum? Yeah, because 0 is smaller than 4. Logically, that's it. Well, let's actually prove it then. So let's look at 0, 0. Draw myself up a little table, x, but instead of looking at the y values, I just want to see what's the curve doing. Is it increasing, decreasing, or what have you? So in the middle there's 0, and I know it's stationary, so it's got a horizontal tangent at that point. We need to pick a point on the negative side, or the left-hand side of 0, and we need to pick a point on the right-hand side. We can pick any number we like. You just can't go past any discontinuity, if there is one. I mean, there's not for this one. Or any other stationary point. So on the right-hand side, I can't go past 2. On the left-hand side, I've got an infinite number of numbers I could choose from. So on the left-hand side, I chose -1. So you write down, okay, this is the number I've chosen to inspect. -1, the derivative turns out to be -9, and I just draw myself a little line, so okay, that's decreasing. I know that's going down. Let's pick a number on the right-hand side. Again, it has to be before 2. I wonder which one I'm going to pick. Oh, what? Oh, yes. +3. Therefore, 0, 0 for this graph is a minimum turning point. Let's check out the other one. Table of values. 2's in the middle. And we know that has a derivative of 0. I have to pick one on the left-hand side and one on the right-hand side. Don't be silly. Use the same number. I'm going to use 1 again because I've already worked it out. Don't, for some insane reason, go, oh, I try 0.5 this time. Yeah. If you've already worked it out, you've worked it out. So that's 3. It's going up. Any number I like from 2 to infinity. Ooh, which one shall I pick? I go 2 all the way to infinity.
2.1.
No, 3. 3. Sub it in. And 2 down. There we go. So we're going up, stationary down, 2, 4, maximum turning point. Okay, let's draw it. 0, 0. 2, 4. That's the graph we're going to draw. Whee! There you go. Done. I said very rough graph. You know, would I bother labelling the x-intercept? Is that what you're about to ask? Look, I probably would with this one because it's quite easy to find. But if it's difficult to find, I'm not going to worry about it. So it's just a rough sketch. This is what the shape's doing. This is where it is.